Okay. Hi, everyone. Good evening. Can you hear me?
Good evening.
Yeah. Can you hear me?
Yes, ma'am. We can hear
Okay.
you.
All right. Great. So, very good evening, everyone, and welcome to the fifth live session for this course. Yeah. Okay. Sorry for the noise. Okay. I will just start sharing my screen, and I think you can see it now. Yeah. All right. So, this is for the fifth week, so we are more than halfway through the course. And so, as always, we'll first quickly recap whatever was taught in this week. We will solve a few practice questions, and then we will go on to take a look at the solution for the last week's assignment. And if there's any question, we can go into that in detail. Okay, before I start the session, is there any question? Any doubt, anything you wanted to talk about? Okay, if there's nothing to discuss before that, I'll quickly start summarizing. Okay. All right, yeah, so this one's just, yeah, housekeeping information. You all are already familiar with, I hope. Okay, so this week started off by a little continuation from the last week's topic of expectation and what all information can we find with expectation of different values. So so we know that the expectation for a discrete random variable is defined as the summation of the product of that variable multiplied by its probability. And in case it's a continuous random variable, you would have its distribution multiplied by that value, and you take an integration from minus infinity to infinity. So now this is by definition, this is expectation by definition. And now you can have different transformations of that variable. So if it's of the form ax plus b, where a and b are constants, then when you are talking in terms of expectation, the expectation takes the form a multiplied by the expectation of that variable x, and you add the other constant b. And expectation of a sum of these random variables, if you have discrete random variables like this, you can just take a sum of the expectations of it, right? So expectation of a sum is equal to the sum of the expectations. But now let's see these things in terms of the variance. So variance is defined as the expectation of the random variable minus the mu, which is the mean, and you take a whole square. So the expectation of the square of this difference, and it can be also written as expectation of square of that variable minus the square of the expectation of that variable. So this thing is something I would really recommend all of you to remember, because this will come really handy in, and you'll see this being used in all the slides of today's discussion. So you've already seen this in week 5, and this will just, it should be like a go-to formula in a lot of things. And so this is definition of variance. And then variance, when you talk about transformation, so if it's of the form ax plus b, now b is a constant, right? So variance is sort of measuring the distribution across, like how different, how spread out the values are about the mean. So now b is a constant, right? So whether a b is added or not, b is going to be added to the mean also. So this constant, uh, it does not matter, right? So if I would just draw it, give me a second. Yeah. So let's say if we just take a distribution like this, okay? And can you again tell me, when I say this is a distribution, what is it on the x-axis and what is it on the y-axis? Do you remember? We discussed this in the first and second week. Normally this is how you see a distribution, right? It's as you might have seen in this week, you'll recall that it is like a normal distribution. So what is it on the X and Y axis?
X-axis will come the variable that is time, duration, or number of days or something, or
Okay.
whatever quality of we are taking, and Y-axis will come the numbers. For
Good.
example,
Yeah.
quantity of
Absolutely.
the
Frequency.
frequency. Yeah.
Yes, correct. Absolutely. Right. So that is good. Right. So let's say if this was your original distribution of X, and if this was, let's say, X plus B. So if X had the mean was mu, now since all the values in this new distribution, you add a B to it. But now you see this range is not changing, right? So if you, which is why the variance of this new transformed variable, there is no mention of B here. But in case if you are now multiplying a value A to each of your variables, if you take a look at this formula, you would come across that the variance is now, it's now multiplied by the square of whatever was added here. All right, so this is also important. And now, so here we talked about this transformation, and the other thing is, if you now have a sum of different random variables, what is the variance? So the variance by default is not just adding up these variances, but in fact there's this second term also here. So this is summing up twice. So it's summing up over all values of X, I, and J. Now here I would just like to tell you, if you have just two values, so let's say this is equal to X, sorry, so here if it is x1 plus x2, right? So then in this case, it's going to be the variance of x1 plus variance of x2, plus now you can take it I and j over all values, right? So it's going to be first, it's going to be covariance of x1 comma x2, and you will also have the covariance of x2 comma x1, right? And covariance, it's commutative, right? So this part is actually equal to twice the covariance of x1 x2. So just this is I'm not sure if this was very clear in the lecture, so just this is how it's going to be. So it's all possible combinations. All right. Okay. And I think there's one more thing. Yeah, so let me I think I can just, can I shift the whole thing down so that it's still there? Okay, wait, I can draw this again. Yeah. So, so this is what the covariance is, right? So if you see, if you remember this is how the variance is defined. So the covariance is going to be, instead of x minus mu square, it's going to be x minus mu and y minus mu, right? So you can just see, if you solve it, you'll come across this value, right? And now this term here, this term, expectation xy, it's equal to expectation x into expectation y if the variables are independent, right? So that for independent variables, covariance is 0. And this is what you can also see from any figure, right? If you make these plots, right? This is x and this is y. If they are all over the place, so that means they're independent. There's no relation between them. So the covariance is 0. And this covariance being 0, you can plug here. And in that case, variance of summation of x becomes summation of variance of individual x's, right? So this thing. So in terms of expectation of the value, the summation rule holds. And this summation rule holds for variance only when the individual random variables, they are independent, right? Was this clear to everybody? Right? Any questions? You can put it in the chat box. You can unmute yourselves and speak. All right. Okay. So if there's no question here, Next, a major chunk of this week's lectures were about movement generating functions. And so where is this coming from? Why do we use it? So here we are defining, now this, you are seeing that phi of a variable t, you're calling it phi of some variable t, that's defined as the expectation of e to the power tx. E to the power tx, or you can say exponent. It can also be written, so you would have seen this being used here. So exponential dx. It's just for an easier notation, because writing something in power, it's, as you can see here from the font also, it becomes it's taking up lesser space. So this here becomes, instead of putting it as superscript, you're putting it just in that same line. So it's just for a simpler notation. Otherwise, these two things, they are absolutely the same meaning. So now from the previous thing, we saw what is expectation of x. So let's talk in terms of continuous variable. So it's integration over the whole range. So ideally that range is minus infinity to infinity. That random variable multiplied by the distribution. And then you integrate it over dx, right? So that's the same thing here. So you're finding the expectation of a whatever the variable is. You're writing that here, right? Expectation, whatever this variable, sorry. Right? So whatever this variable is, you're putting that here, and then that's fx dx. And now what is this t basically doing here? So, okay, so before we go into that, it's a different, it's an integration form. Now, definitely you can take a differential of it. It's like a polynomial. You can take a differential. And now an important thing to remember here is that, so the now here, what you're doing is you're taking, so the the differential here is in terms of t, right? You're taking d by dt of e to the power tx. Now imagine, so when you're taking a differential with respect to t, x is considered to be a constant. Now, normally what we write is d by dx, let's say it's e to the power 2x, right? This is very, like, this is a simple exponent. So how is it dealt with? So this 2, it comes out as it's, you take it down, and the rest of it remains unchanged. So this is the formula for differential, when you want to find the differential of e to the power something, and it's like a, in terms of x, with respect to x. Now here, when you want to find the differential of tx, now you think about it like this. Let's write it as x and t. So now t is that variable of yours, right? Which, with respect to which you want to find it. And x is considered to be a constant. So here, like 2 came down, here we'll just take x. We'll just take out x, and everything else remains unchanged. Okay? So this is what came here, right? This is what was there, e to the power tx. And everything else remains the same, right? Because fx here, fx is a function in x. It is not a function in t. So that is also considered to be a constant. Constant when you are differentiating with in terms of x, right? So here you're talking about two variables. So those of you who are familiar with differentiation and integration, you can appreciate that. So just take that into account. In case this is new to you, I can only recommend that then it is these formulas that you will have to remember, right? So that you can just think about what the correct formula for a particular question is, right? Because explaining differentiation and integration in the live sessions would not be possible. But if you're interested, you're more than welcome to look for resources that will explain you these, right? So if nothing else, class 11th and 12th maths is your go-to resource, right? Those textbooks, they can really give you an idea of how it's done. Okay. And so this is when you find the first differential. You do the differentiation once. So you get this. Now, again, you do the differentiation. So you do d by dt of x e to the power xt. There's also this fx term, but I'm ignoring it for the time being because it's a constant. So it's just there as it is. Now, when you're doing this differentiation, x here is a constant. So think of this x as this 2, not affected. But now you are differentiating this part. So same as before, what happens is this x, which is a constant, it comes out. So x multiplied by x, this gives you x square. And then this e to the power xt, this stays as it is. So this is this term, right? Now, okay, so you defined this phi, right? Phi of t is expectation of e to the power tx. So expectation, you know the formula in terms of sigma, in terms of differentiation, that's done. But and now you also find the differentiation. Now, what is the, why did we go through all of this? So this is in terms of t, right? Now, if you plug in the value t, once you have found the differentiation, once you see this, it's, you will say that, so now when this t is 0, right? Now this t 0, so e to the power 0, anything to the power 0 is 1, right? So what you get is x fx, right? And what is fxx? F, like x fx, that's the expectation of x. So sigma, so the differential of, not sigma, the differential of phi at t0 is the expectation of x. Likewise, the double differentiation of phi at t0 is the expectation of x square, and so on and so forth. So whichever differential you take, and when you say that you've taken the differential at t is equal to 0, it's that expectation. So this is going to help us in for all the upcoming 5, I think 5 different distributions that we look at. So you'll see that for all of them, once you're able to calculate this moment, these one, especially these two differentials, that will easily give you expectation of x and expectation of x square. And why are these two important? Because we know that the expectation of, okay, it's not written here, but expectation of x is actually the mean, right? And likewise, the variance can be obtained through expectation of x square minus square of expectation of x, right? So you will be able to calculate both mean and variance of any distribution if you take use of this funda. Okay, so now we'll just quickly go through all these examples. Any question till now? Okay.
Ma'am, which one to consider as a final formula if some question is asked from this?
Yeah, so so that will depend what distribution the variable follows, right? So we'll see, I mean, there are certain sort of, either it's going to be explicitly mentioned in the question that this is the case and this variable follows normal distribution, or this follows Poisson distribution, as we just see all these distributions. But in some of them, especially in case of binomial distribution, you will be able to see it by the nature of the question itself. So let's see how that is. Okay, so now here, the basic idea is, so a Bernoulli trial means a single trial, right? Singular. So it can happen. So it's basically, there are two options. Either it's going to be success or there's going to be failure, right? When there is such an option, such a thing happens. So one time it's happening, and you have two options of two. There are only two options that can happen for a given trial. Now, how you define that trial would depend on the question, but a single event, it can be either happening or not happening with different probabilities, as in the two events will have individual probabilities adding up to one. And that thing can happen several times. There are several trials that are going to happen. And then the nature of the question will most likely be such that you are interested in that success happening, this success happening a particular number of times, right? So you're doing the same thing, let's say 10 times, and you are interested, right? So it can be like, let's say success, failure, right? So let's say like this. So here it's 5 and 5, right? So 5 successes and you have 5 failures. Now 5 failures is, it's right, that 5 plus 5 10. So n is going to be the number of successes plus number of failures naturally. But what you're more interested in is, out of those n times, how many times, so you're interested in, out of n, let's say how out of 10, success can happen 5 times. So this is one option. So basically this is like an automated version. So you remember, you in the previous weeks we were talking about permutations and combinations, right? So here you can say that this thing happening, there are how many ways in which it can happen, right? So you can take a permutation that success can happen 5 out of 10 times. How many different ways are there? What are the exact, right? Imagine each of this being like a position, which event is happening. But on top of that, it is also important now that success and failure, it's not half and half. So they have individual probabilities associated with them, right? P and Q, where P plus Q is definitely equal to 1. So now, in such a case, just the automated version gives you what is called the binomial distribution. Okay. So in this case, basically what we are saying is you're summing up, right? Each of these events, for all of this single thing is a trial, right? So for one trial, you'll say it's a success, like score 1, and failure has a score 0. In heads and tails also, when we talked about expectation, it can either be a head or a tail. Now you can assign 1 and 0 to any of them. So the expectation that turns out to be half, because it can, right? Because then whenever you're talking about binomial, you would always see the score as 1 and 0. So if it's just one trial, the score is going to be half, because it can be in either of them are the only options, right? And now for each of the distributions, so this is like, this is the idea of the distribution. And here in these slides, I have summarized the expectation and variance which sir derived in the course for each of these distributions. So now it is up to you what you prefer. Would you prefer deriving it, which is time consuming, but you don't have to remember as much? But and then these formulas are also there. So with a little practice, you can try questions, uh, try solving the like, for example, the assignment questions and all that. So you will get an idea of why this could be slightly, you'll actually see this being a little intuitive also, right? So let's say now we talk about the expectation. So think about this in terms of the coin toss, right? So in terms of coin toss, right, now think about it. Normally what we consider is that the probability of heads is half and the probability of tails is also half. Now let's say we are calling heads to be the success, so we call this as P, and this is going to be Q normally. So now I am interested in the expectation value, right? Now if I toss it 5 times, my, so it's going to be, so it, when there is one trial, the expectation is 0.5 or half. If there are 2 trials, so again I can have, so there are, the possibility is I can have 0 and 0, as in tails. I can have 0 and 1. I can have 1 and 0, and I can have 1 and 1, right? So so in this case, it's the sum is 0. Here the sum is 1. This is 1. This is 2. And so basically in 2 trials, the average expectation is basically like the mean, right? The average. So average is 0. Here the average is 1. And here in this case, the average is 0.5. Right? And now if you take the average of the whole thing, so 0 plus 0.5 plus 0.5 plus 1, this is 2, and 4 things, again 0.5, right? Actually, I should not have taken this half here. Okay, wait. I think I'll just confuse you with this thing here. So, okay, so what I wanted to say with this expectation thing actually is, so in terms of the coin toss, if you toss it 2 times, you can have the heads coming up. So consider 0 to be tails and 1 to be heads, right? So if you have 2 trials, 2 into, so from this formula, n is 2 and p is half, which is 1. So let's say if you're saying 1, 2, 3, 4, 5, 6, 7, 8. There were 8 options. And so out of these 8 total things, you got head 4 of the times, right? So 4 out of 8, that is half, right? Or you can say, so, okay, I'm not able to exactly explain this, but so the expectation is between 0 and 1, right? So here you got none of it worked. Here you got it 1 time. Here you got it 1 time, which is half, right? So you did not get both heads, but you got half and half. Here you got more number of times, and here you got less number of times. So the basic, it's staying at a middle point here, and that midpoint is happening because the probabilities were at the midpoint, right? They were half. Now imagine if this was a biased coin toss, and if the probability of heads was higher, there was a higher chance that it would not have been just, the options would have been this, but the distribution would not have been uniform, right? So this is why in terms of binomial distribution, the expectation value, so for 1 trial it's 0.5. For 2 trials, it becomes 2 into 0.5, which is 1. 3 trials, 3 into 0.5. But in terms of, if you don't have a biased coin, if it's p any other value, the expectation would be n times that value of success. And if so the way it has been calculated, you would also see that the variance comes out to be npq. So it's just a product of the 3 numbers that are there. Okay. This is there. And then this is also just one more formula, that the probability of this thing happening. So you're taking out of n, you're interested in R trials. And if you're interested in success at R plus 1, so it's just a slightly more simplified formula. So you don't need to calculate the whole thing. So if you have been given P, let's say, number of success R, and if you want to calculate P number of success R plus 1, so you can just use these simple formulas instead of calculating NC, R, P to the power R, Q to the power N minus R. Okay, so now when are you going to use binomial distribution? When you have, you can define that there is a trial, there is one event which has 2 possibilities, success and failure, and you are interested in multiple such trials, specifically a lot of such trials, and how many times out of in those multiple trials will you be getting success. When that is what the question demands, you can identify that this is a question for binomial distribution. So it's going to be one of some of these formulas that you're going to apply. Okay, so now we come to the next distribution, which is point search distribution. Okay, now So this is a formula, e to the power minus lambda multiplied by lambda to the power x factorial x divided by factorial x. And this one is for discrete random variables only, and they have to be greater than 0. So it's, I mean, 0 and above, right? Because a factorial is not defined for negative, negative variables. So this is important when you think that this is the kind of values that your random variable accepts. Then you can think that probably it's a question for Poisson distribution. And here, both the expectation and the variance is this value lambda. Okay. And as in the case of the previous distribution, here also you have a formula. So this you can also derive. This is simple arithmetics. Okay. You can just calculate p x, I mean, write the formula for p x plus 1. So you replace x with x plus 1, and you write the two values of probability, you divide them, and then you'll be able to cut out most of them. You'll be able to cancel most of them. So this is what is going to remain. And now if you see, you'll see that when the value of uh yeah, so when the value of n, which we saw in the previous case, when you have a very large n and a very small p, then in that case, binomial distribution starts behaving like Poisson distribution, where what happens is the product NP is actually equal to lambda. So now instead of using that formula, you can use this formula where this lambda becomes NP. Okay. All right. Next distribution that was discussed was uniform distribution. As the name suggests, uniform distribution is basically, it's a particular value. Now what this particular value is depends on across what values are we looking at, right? So now basically here we are taking probability, right? So the basic like a restraint, like a not a like a constraint on probability is that this the probability across the whole range. So the whole of probability has to be 0, right? Across the whole limit, right? So at any particular point, so if you okay, yeah, so probability, this is the formula of probability, because now if you multiply this, so you'll see that so this value becomes 1 by b minus a for your range a to, let's say, for range a to b, right? For when x is between these two ranges and it's 0 otherwise, so that the summation gives you 1, right? And the expectation is basically the midpoint of this two, right? You expect, if this is the range, if you say that my variable can be between a and b, it can only accept these values, then you would expect the expectation, which means the mean, is going to be this thing, right? This is your expectation of x. And your variance of x, which you can also derive, is b minus a whole square divided by 12. Right? So this, I think, was left out as a question in the lecture. So this is that formula of variance. Okay. These formulas are all there for your reference in the PPT. I'll upload the PPT to the Google Drive after today's session. Yeah. And then we come to normal distribution. And normally this is how you write normal distribution. So like we saw all the previous distributions, they are defined by certain variables, right? So binomial distribution, you should be knowing what is P and Q, and then N and R is case specific, right? So N, R, P, and Q, these are the values which are defining binomial distribution. In terms of Poisson distribution, it's mainly lambda that you would be interested in. In uniform distribution, it's this range A and B that you want to know. In normal distribution, as is for any other distribution, you are interested in mean and variance or mean and standard deviation, and this is what is actually defining normal distribution, right? So it's of this formula where this is no-brainer. Expectation is mu, variance is sigma square, which is sort of by definition, but to take a look at the derivation, it's a relatively lengthy derivation, but it was there in I think it was in the second last lecture of the week. Yeah. And so here, this is also slightly important to remember. Okay. So as was the case in all of the other distributions also, the expectation and the variance were derived using the formula of the phi of t, right? So phi of t is this, and you can differentiate it once, then put in the value t is equal to 0, so you'll get mu. You differentiate it twice, and then you put the value t is 0, you'll get expectation of x square, right? And then you subtract these two, so you will get the variance, right? That's the formula for variance. And this is also an important derivation. So again, it would not be possible to discuss the whole derivation in the session, but if you are interested in finding the probability of x being between two values and this variable follows normal distribution, then this formula where you find out the phi of b minus the mean divided by standard deviation and subtract it with this value, right? So these two values you're plugging in here, that's going to give you the probability. And also one more thing. So this was also given in the lectures, right? So this is normal distribution. This is sigma. And now let's say this is, so the way it's defined is, so what is this phi actually telling you? So when you're saying phi of b minus mu by sigma, or phi of whatever the term is, it means, phi of x, or I should say, phi of x is equal to capital X. This basically means probability of x less than capital X, right? So that means if here I'm saying this is x, so it means it's this region. Now, actually, let's say this is 0, right? Because here it's like you've normalized it. You remember the discussion on scaling and centering the data. So b minus mu is actually centering your data, right? And once you are dividing this by sigma, you've actually scaled your data. Yeah, scaling it so that now the standard deviation and the variance is now 1. So once that happens, if it's centered, right? So now you can see, now this probability and this probability is the same. So how can you write this one? This shaded region is actually this one, right? Probability of x less than, instead here it's minus x. So that becomes sigma of minus x. And this probability is actually the whole of it minus this larger region here. So this is 1 minus sigma of x. And since these two, it's a symmetric distribution, so these two values, they are equal, and this is what shows here. Okay. And so for x, if you are taking a lot of different random variables, all of them following normal distribution, and you have another variable x, which is the sum of all these normally distributed random variables, then the mean of all of them is the sum, and so is the variance. This is a special case when you have normal distribution. Another important part of normal distribution, which was also discussed previously, is that for such a distribution, mean, median, and mode, they are all the same, right? So there is no skew. It's a symmetric distribution. Okay. And I think this one is the last distribution that was discussed. This is the exponential distribution. Now, just a word of caution, do not confuse between Poisson and exponential distribution. Yeah, because they have somewhat similar formula, but so Poisson distribution is for random variables, 0 and above, for discrete random variables, 0 and above. And exponential distribution, it's not for discrete, it's for continuous ones, right? And here the expectation and variance, the expectation is 1 by lambda, and the variance of such a distribution is 1 by lambda square. So I think, yeah, this is all that was discussed in the week. There were a lot of examples given. So you can, so let me know if any of those questions you want me to discuss. But before we do that, there are a few questions, very simple ones, but we can just go through these for now. So, okay, so this one we just talked about. Which one is it? For which distribution are the mean and median equal? Hello, are you all still with me?
C.
Yeah, right? Normal distribution.
Normal distribution.
C and D. So why do you say normal distribution? Why do you say, sorry, uniform distribution?
Because the portion, like if we consider the center 0, where mean is there, the amount of data that lies before the center and after the center has an equal range. For example, the SD that we tell.
Okay,
Plus,
okay. Yeah, yeah, yeah. Oh,
in that way,
that's
it becomes a uniform distribution.
that is a good point. It should be the case, right?
Yeah.
Yeah, okay. Good. I actually, that skipped my mind. Okay, good. So yeah, both of them would be the correct answer then. All right. Then if X is uniformly distributed, so now such would be some cases where you are simply shown, you are already given that out of the 5 distributions that were discussed, uniform distribution is what you're looking at. So what is the probability for any point to be between 0 and 100? How would we solve this? What formula do we use? Why do you say 0.1? How did you reach 0.1? Can you explain? Or anybody, what do you think the answer is? Is this correct? Right. So,
1.
okay. So now, so the formula is probability is, let's say, whatever your points A and B are. And this one is between the whole range, right? So I think when I wrote it, I wrote A and B both the places, but this is like, let's say the total range. So beta minus alpha. For example, I'll just write this again. So let's say a distribution is known between, let's say alpha and beta, and you are interested in A and B, right? So this is the whole range. And this is fx, right? This is basically this thing. this whole term is your fx. Now the constraint on probability is, what is the constraint? That the probability over the whole range should be 1. Right? So this whole thing, so when you have, right? So this value is actually 1 minus. And why does this work? That's because when you have the whole range, beta to alpha, sorry, alpha to beta. So 1 minus beta minus alpha dx. Now when you integrate it, what happens? So 1 minus beta minus 1 by beta minus alpha is a constant. So the integration dx from whatever numbers we are talking about, that becomes x by, so x, and you are taking this range, right? Now when it's the whole range, so this becomes beta minus alpha divided by beta minus alpha. So it's 1, which is good. Now in the case which is asked for any point, let's say the point is C. So now you want to find the probability of the point C. So the integration is taken from C to C. So from C to C, 1 minus b minus a, beta minus alpha, whatever you write it. So that's basically x from C to C, b minus a. So that's basically 0, right? And why is that the case? So this uniform distribution, it's for a continuous variable, right? So the probability for each of the points, now you can have infinite points between alpha and beta. Each of the infinite points have a certain probability associated with it. If they have a probability associated with it, so what multiplied by these infinite, or rather summing, what number are you going to sum over infinite points that's going to give you 1? Right? So there's a value, let's say small p, you're solving plus small p. If each of the points, each of the infinite points, they have a probability p, you sum this infinite times, and that should give you 1. Is there any number that you add infinite times that gives you 1? No, right? You can't have a number that you add infinite times that's going to give you 1. Right? So the probability at any point is 0 at a single point, but the probability of an interval is defined. Okay? So the answer is 0 in this case. Was this clear? Yeah?
Yes, ma'am.
Okay, all right, good. So this is one of the trick questions that can be asked, right?
So if it is told at any point, then like whatever it may be, the answer would be 0 only.
Yes, because any point, a single point, when you're talking about continuous variables, non-discrete, when you're talking about continuous random variables, any distribution at any point is going to give you 0. This is why you do integration, right? So this is not limited to uniform distribution.
Okay.
So because whenever, if I draw anything here, okay, let's say, think of it in terms of just like geometry, right? So if you say that, so you can define the area of this chunk, right? You can say this has some area. How would you say? So let's say if this was a rectangle, you will say length into breadth. That's the area, right? So how is integration normally done? You divide it into very, very thin rectangles, right? So, and you just sum them up. But now if I say you want to find the area of this line, the line does not have an area, right? Rectangles, any two-dimensional figure will have a area, but a single dimension area will not have an area, right? So when you say a point, you are integrating. So this thing here is fx. The integration gives you probability, and integration for a single line is 0. So the probability at a point is 0. Okay. So had this been uniform distribution, had this been normal distribution, had this been exponential distribution, it would have been 0. Had it been this one, Poisson distribution, it would probably not have been 0 because it's defined for discrete variables. So at any given point, right? So at any point, it's defined for each of the points. So then you would have to find out the probability at that point. Okay. All right. Next we come to this question. Now I would like you to solve it very carefully. There was something I told you in one of the first slide of today's discussion, right? So give it a try, take a minute or two, and then I will solve it. Are you able to solve it? Yes, 7 is the correct answer. So I will just quickly tell you the formula in case you're having a hard time recollecting it. So the formula was that variance summation x is equal to summation of variance of, let's say, xi plus covariance xij. This is what the formula was. Sorry, right? So now this thing, variance, so here xi is basically I and j, you have 1 and 2, or you have x and y here. So this is 35. And then you have summation xi's, which means you're adding the variances. So you have 15 plus 6. And now this we want to see. Now for two values, when you have 1x, like x1 and x2, you're going to have this as twice the covariance of x and y. Now this becomes a simple algebra question. So 35 is equal to 21 plus 2, we'll call it x. So 2x is equal to 14, therefore x is equal to 7. So covariance is 7. Yeah. Okay. What was this? Was this fine? Okay. So this is the next question. What is the value of expectation, which is ax, for a binomial random variable where n is 10 and p is 0.6?
Can I ask here one thing?
Sorry. Yes.
Yeah, so in the last question here, so I got your like what you were trying to make us understand. So why you have mentioned the variable x both the time, because since the variable y is also there, right?
Oh, so this I have written as the general notation. This is the formula.
Okay.
Right. Now, here I've written xi and xj. So basically, you have two variables. If this is written as y, you can also call this x as x1, y as x2.
Okay.
Right? So basically, two variables. And
Yeah,
all
so
possible. So
the variable x summation of xi equals to summation of variable xi, right?
say that again.
No, the formula here, could you please explain this equal after the equal to, what is that?
Yeah. So here it's, so you want to find the variance. If you want to find the variance of a sum of two random variables, which is this, right? This is how you would write variance of a sum of random variable. You're defining a third variable, which is the sum of two variables. You want to find the variance of that. So that can be written as sum of individual variances. This is just an extra mark. Yeah, so sum of individual variances. So that is variance of x1 plus variance of x2, like here, x and y. And then you are summing up for all possible combinations of the whatever values are there. So let's say if there were three of them. It was not xy, it was x, y, and z. So in how many ways can you write? You can write x and y, you can write x and z, you can write y and x, y and z, y and z, z and x, and z and y. So this would have been 6 possible combinations, right? Where this and this is the same, this and this is the same, and this and this is the same. So you're basically going to write twice of covariance xy plus covariance xz plus covariance zy. So here we just have x and y. So we have twice of x and y.
Yeah, thank you so much.
Okay. Okay. Yeah. So what is the value of the expectation for a random, for a binomially distributed random variable? Do you remember the formula? NP, right? So just multiply this. So 6.
Yeah. Excuse me. The
Yes.
last sum, you had used only x, no? There are two variables, x and y, but you have written it as 2x.
Oh, okay. No, so this x, I just meant covariance. Covariance xy. Therefore, twice of covariance xy. Therefore, covariance xy. I was solving it in terms of algebra, right? So covariance
thank you.
xy is 7. So that's what our answer is.
Okay, thank you.
I'll just, yeah, okay, thanks. Okay.
One more doubt. If it is 3 variables, what will be your answer?
Yeah, so this is what I told you. I'll just write it again clearly.
What you will get, I'm asking.
Yeah.
14 by 3, or it's the same thing?
Would it be what?
No, you put it 14 by 2 is 7. It's 3 variables, so it will be about 14 by 3 or?
So in that case, so let's say if I'll just tell you, so then the formula would be variance of x plus y plus z. So you have these 3 variables, right? That is equal to variance of x plus variance of y plus variance of z. So that becomes this term, right? Summation of individual variances plus this is going to be your covariance xy plus covariance yz plus covariance xz. This is going to be that formula.
No, the same value is given. I'm asking you, but
so here you want to find covariance xy, right? Now we don't have variance of z known.
Z value we don't know.
Yeah, we don't know all of these now, so we can't solve it. But this is the formula that we are going to use.
Okay.
Again, 2, yes. So you see, so why did we have 2 here? Because this is a double summation sign. You're taking, so x and y also you're taking, and you're taking y and x also. Right? So you're taking all the covariances twice. So this is why all the 3 possible covariances, x, y, y, z, z, x, and you're taking it twice.
Okay.
Yeah?
Okay.
Okay, all right. And so this one gives us 6. And yeah, correct. That 10 into 0.6 is 6. And if x is normally distributed, okay, now here comes the other question from as the one we just saw. If it's distributed between 0 and 200, now what is the probability of x lying between a range? Now you can solve this, right? So we have 1 minus b minus a, and you are summing dx from your some let's call it m and n. Now you need to carefully just define what it is. So b and a are your whole range. So that is 200 minus 0. and some integration dx gives you x, and that is going to be over the range 20 to 80. Yeah, so that becomes 60 divided by 200. So that's 3 by 10. So that's 0.3. Yeah. That's the answer you got, right? Sorry. It's not 0.33. It'll be just 0.3. Okay. All right. So I think with that, we come to the end of the things I had put this week. And okay, we are good on time today. So if you have any questions, just let me know. Otherwise, I'll just open the week 4 assignment solution that was released and we'll just go through it quickly. All right. Any question? I am not able to hear you.
And week 4 assignment was like I was not able to keep the proper formulas at a proper place itself.
Okay. All right. So let's go through the questions and let's see.
If you can just see that if such questions are, because I was not knowing that okay, what exactly which formula I'm supposed to put in here and how I'm supposed to solve that. So
Okay.
and
Okay. Let's go through the questions and you tell me what you thought about it. So what,
okay.
right? So we'll see. Okay. We have a lot of time, so we can spend good time in discussing this. Okay. So the first question. Yeah, sorry. Yes. Yes.
Can you please open the binomial distribution slide?
Binomial distribution. The
Poisson distribution.
this one?
Yes. So the last time you mentioned about the large n minus small p. So lambda equal to np. In that case, the binomial distribution approach is Poisson distribution.
Yes.
Then if in case of Poisson distribution approaches to binomial distribution, then what about n and the p?
Say the last thing again. If Poisson distribution approaches binomial, then
if large n and for small p, binomial distribution approaches, that means it is similar like Poisson.
Yes. Yes.
In other case, if you want to see Poisson distribution similar like binomial.
Oh no, in other it is not. So actually I should have put the plots for it, but maybe if you want, we can actually search that on Google and we can just check. So the binomial distribution and the Poisson distribution, they look different. So they are dependent on, so let's say binomial distribution, it's dependent on what is n and what is p, right? So at values where n is large and p is very small, in those cases, the binomial distribution, that plot is going to look similar to the plot of Poisson distribution. So that is what here it's shown. So you can use this formula also to calculate the probability. You'll just, instead of calculating probability from here using this formula, you can calculate probability from here where you are just putting NP instead of lambda. The other way, I don't think that happens, that at a particular value of particular type of n or p, I don't think binomial distribution approaches Poisson, or at particular values of lambda, I don't think Poisson distribution approaches binomial.
But in video sessions is not proven for large n and small p, lambda equal to np, probability of Poisson variable is very similar to probability of binomial
Yes,
random variable.
yes, that's the meaning.
I think so. Poisson distribution is similar to binomials, are told
Yes.
in the video session. But you are telling binomial distribution is similar to Poisson distribution if n is and p is small.
So binomial distribution is defined by n and p, right?
Yes.
So you can have binomial where n is small. Let's say n is only 10 and p can be 0.5, like 10 coin tosses. So in that case, if you plug in here, it will probably give you very different values. But when, let's say, n is 10,000 and p is maybe 0.1, then if solving it through this, if suppose that is very difficult, but solving it with this formula becomes simpler, and if you actually use this formula, then you would get very similar values of probability. This is why we are saying that for particular values of n and p, binomial distribution approaches Poisson distribution. I think I'm missing the point that you're saying here. Can you ask the question again?
So for large n and small p, you told binomial distribution approaches Poisson distribution.
Yes.
So as per that slide.
Yes,
But in the
right.
video sessions are told for large n and small p, Poisson is very similar to binomial.
Okay. I would reframe it this way, because when you're putting a constraint on n and p, you're talking about binomial distribution, right? You're not talking about Poisson distribution. So the thing is that at particular these values, the probability you get using both the formulas is very similar. So you can say it in that context also. But both the sentences are aiming to say the same thing. That at these values you can define binomial distribution, right? You can't. So this is not normally happening. This is only happening at particular values of n and p, and that particular values are a large value for n and a very small value for p. Right?
Quite the contrast to what you told and what is mentioned in the video sessions. So for large p and large n and small p, we are telling binomial similar like Poisson. But same parameter, large n and small p, the video sessions are told. So Poisson is similar like binomial.
I understand.
Condition is same for large n and small p. Condition is same. But SAR told Poisson is similar like binomial, but you are telling binomial is similar like Poisson.
Yeah. So what I think, what Sir said and what I am saying, they are the same thing. We've just said it in different ways. But I would actually like to explain it using this statement here. Binomial approaches Poisson, because you are putting a constraint on n and p, right? And n and p defines binomial. N and p does not define Poisson distribution.
But of course, what we are connecting and again n and p related to lambda.
We are saying lambda, and then we are saying in that case, if you consider lambda to be np, and why are we considering lambda np? Because np there is the expectation.
Lambda terms are completely related to Poisson, and n and p three terms are related to binomial.
Yes.
So
I'll just tell you a third way then. So the thing is that Poisson distribution, you can have different values of n, different values of p. You can have different, let's say, different plots made. Poisson distribution, you'll have different values of lambda, you'll have different plots made. Now, for some particular value n and p, where n is very large and p is very small, you would get a certain distribution. And when you multiply these numbers, you would get a certain value of lambda. Now, when you compare these two plots, you would see that these plots look very similar. So now it's up to you to say, I mean, you can define it in either way, right? Binomial is approaching Poisson, Poisson is approaching binomial. Because
so
of this,
statements are both are same only.
as far as my understanding goes, I would say both the statements are same.
Means for large n and small p, binomial is similar to Poisson or Poisson is similar to
Yes.
binomial. Both are
Yes.
same statement.
Both are same
Oh,
statements.
okay. So does it
Yeah.
having any difference?
No, it's the same statement. Yeah. Okay. All right.
There is no vice versa in this case, no?
It's as in, for
Like
example?
for example, large n and small p, for like something, or vice versa. It's something
Oh, no,
doesn't change, no.
no. Small and large p, no, not like that. This is only one condition. Yeah. Okay. All right. So let's start with question 1. So you consider a population, these numbers. What is the probability of finding an even number less than 20? So this one's straightforward, right? Which ones are the even number less than 20? 2, 6, and 12. So you have 3 as your your favorable outcomes. And how many are there in total? You have 9 in all. So 3 out of 9. That is 1 by 3. So this is your probability. So D is the answer, right? Now question number 2. The answer that has been marked correct here is not the correct answer. So this, as you can see from, if you take a look at the discussion forum, this has been sent for remarking. So both the correct answer and the incorrectly marked answer here will be given the right answer here. So how are we going to solve this? So now I would like you to, I would solve this question in 2 ways for you to, just for a better understanding. So I'll go to the slide and I'll just put it there, okay? So the question is that you are drawing one card from a deck of 52 cards. And what is the probability of getting a jack knowing that the card is black? Okay, so just in case if any of you are not familiar with playing cards, because when you talk about probability, use of playing cards comes very frequently. So I'll just give you a quick recap since we have time. I'll just spend a minute on this. So there are 52 cards and they are divided into 4 suits. Okay. Now 2 of them are red. So one of them, this shape like this, not that it's important, but this is a diamond. And the other is the heart. And then we have the black one, which is, this is the spade. And then here it's the club. Do we have a question here? Yep. Good explanation. Okay. Thank you. So these are 4 suits, right? And in each of the suits here, you have 13 cards. So 13, 13, 13, and 13. And what are these cards? This is ace or 1, alternatively 2, 3, 4, 5, 6, 7, 8, 9, 10. And there's jack and queen and king, which is like 11, 12, and 13. Right? So these are the playing cards. So you have 13 in for each of these suits. Right? Now you can see 2 of them are red and 2 of them are black. Okay. So now the question is that you draw 1 out of 52 cards. So you need to find the probability of getting a jack given that you have a black card drawn. Okay. So now, first of all, now
So this
forget.
becomes a conditional probability.
Yes. So like I said, the question answer is incorrectly marked. So you forget the answer right now. Let's just solve it as a question. And you're correct. It's a conditional probability question, right? What is the probability of drawing out a jack given that a black card is drawn? So, so now, how would we solve it? Can you tell me what would be the formula that we use?
P of A intersection B.
P of P of J into P
A
of
intersection B divided by probability of B.
Yeah. Right. All right. I'm not able to hear anybody if you're trying to say some answer.
No, some mic needs to be muted, yes.
Okay. Yeah, okay, it's already muted. Okay, yeah. So now the probability of J intersection B, which is Jack and black. So how many black jacks are here in this suit?
2.
Two of
Two.
them, right? One from spade and one from clubs. So 2. So when we are talking in terms of probability, it's going to be 2 by 52, right? And probability of black cards, how many black cards are there?
26, half the pack.
26.
26, right? So therefore it is 2 by 56, sorry, 2 by 52, and this becomes 52 by 26. So that's 1 by 30, right? So as one of you had rightly written this, right? Now the other way that is just for your like a better understanding. So we
Excuse
have
me.
this. Yes.
Should be divided by 52 numerator. Jack, probability of
Yeah.
Jack among black cards or among the entire card set?
Yeah. So this is not among, this is intersection, right? So blackjack.
Yes.
When you're talking
Okay.
in terms of numerator, so that's exactly what I'm going to talk about now. So what this
Yes.
means, so when we're talking in terms of conditional probability, we discussed that when you are saying that an event has already occurred, it basically means you have now reduced your sample space. So earlier your sample space was 52, right? Earlier, as in for individual events, your sample space is 52. But now you're saying that an event has already occurred. The event is black card. So black card has already been chosen. So now your sample space, earlier your sample space was 52. But now your new sample space is actually 26 only. Because now you know it's a black card. So you just forget about the red cards. And now you're saying what is the probability of drawing a jack out of the black cards? So out of these 26 cards, how many jacks are there? There are 2 of them, right? So it's 2 out of 26, which gives you 1 by 13. So this 1 by 13 and this 1 by 13. So here what we did was we said 2 by 26 because we are saying we are reducing the sample space here. And here it was 2 by 52 because here we are just saying that the 2 events have, like, what is the probability of both the events happening. So blackjack being chosen out of the whole space. So this is actually important, that here you should not end up saying 2 by 26. So this is important. So just like a sanity check, if you are able to solve it in these 2 different ways, if the question, if you're able to do it, I will recommend that you solve it in both the ways so that it becomes clearer to you that, and you're 100% sure that the answer is correct. That's how I would solve it. So the question here actually, here they have just left it at this point, 1 by 26. So the question is going to be regraded. So while A is the correct answer, since B was graded as the right answer, both A and B will be considered to be correct. So this is going to be regraded. All right. Okay. Now the next question is,
Why will B be considered correct?
because they have marked it already, hence.
That's not right.
Yeah.
They'll change that B anyhow.
I as far as the discussion that I saw on the group, B will also be marked. Because that was the initial idea of the question.
No, madam,
That-
practically showing that solution, then how B also is the correct answer for this?
Yeah, it is not, but the question was framed to give you, it was only supposed to sort of give you the probability of the numerator that we just saw, right? 1 by 26. So, which is why B will also be marked as correct. That's as far as I know until this meeting. I can confirm if that's going to be the case. Yeah. Okay. So, yeah. So the next question is that a team has identified 4 different protein subunits. So you have So a protein is, so basically a functional protein is made when 4 smaller proteins, they come together. So that's that group or that complex. So they each of these 4 individual proteins, they are called subunits. So there are 4 different subunits that on association, on coming together, they give you a functional protein. And each of the subunit is connected to the other in a linear fashion. So one after the other. So on further analysis, it was determined that the 4 subunits do not follow any particular arrangement. So any arrangement could actually work. So how many different isoforms or how many such arrangements are actually possible for this protein? So now the question here is, do we go for permutation or do we go for combination, and why? What
And
would
there is
your...
no arrangement, like no particular arrangement is there. So we do not worry about the order. So
No. So here, when it says that
The factorial of 4.
it would be like we would be going for which combinations we can.
Okay. So now tell me, if you have 4 subunits, how many combinations are possible taking all 4 of them?
4 factorial.
4 factorial. Factorial of 4.
So 4 factorial means you are taking into consideration the arrangement. Right? So I would just again so I'll just give me a second. Okay, so here now here you have these 4 subunits, right? Now we say that permutation is for when the arrangement is important and combination when the arrangement is not important. So now tell me, if the arrangement is important, you have 4 proteins, you want to take an arrangement of all 4 of them together, right? So what are we going to write? NPR, what is N, what is R here?
N is 4.
What is R? How many are you taking at a time?
4.
All 4 of them, right? Correct.
Yeah.
So this becomes 4 factorial by 0 factorial. And we know 0 factorial is 1. So this is 4 factorial. And combination 4C4. Right? So this is 4 factorial by 4 factorial by 0 factorial, which is 1. Because there is only one way you can take all 4 of them. Once you've taken all 4, you've taken all 4. There's no other way. Right? So now in the question, the 4 subunits do not follow any particular arrangement. That means all the arrangements are possible for the protein. This question is not in terms of permutation and combination. This statement here, this statement is indicating that they are connected in a linear fashion and there is no restraint on that linear fashion. As long as the 4 proteins are there, the protein, that functional protein is going to be there.
Yeah, that means that, for example, A, B, C, D are the proteins.
Yes.
4 times A can be at the first position, 4 times B can be at the first position.
No.
Like all 4 of them we can combine in a different combination.
So you
for
can
4
have
times.
So you can have ABCD, you can have BACD, you can have BCD, and all of these.
Yeah.
So that is what is 4 factorial, right? 4 into 3 into 2 into 1.
Yeah.
Right? So which
So
is why you
but
have...
here, like for example, one thing is that they have not mentioned that like similar proteins or something, but if the similar question comes, that what sir told, for example, that some book or something has to be there, that has not to be repeated like that.
So here
so in
also,
that case,
so the thing is now, that's a very good question. It's not explicitly mentioned here in the question, but you can say that there are 4 different proteins, and when they are together, they give a functional protein. Right? So if they are 4 distinct ones, So all 4 of them are doing a different job. Generally, that's how a protein works. Each smaller part of a protein is doing a different task. So now you say the protein does 4 tasks because of the 4 subunits. Now, if you don't have one of them, if you sort of repeated one, then the protein is not functional exactly, right? So there are 4 different subunits. They need to come together in any order. So it's a simple permutation of the 4 proteins. Yeah. Okay. Okay, so now the next question. So there are 25 samples which are obtained from cancer patients. 10 of the samples are of early stage tumors and the remaining are of late stage tumors. So that's the distribution, right? 10 plus 50. Now, if 10 samples are selected at random for a research study, what is the probability that all the 10 of these samples will be of late stage tumors, right? So this is very similar to that committee example that keeps coming up, right? So total samples and your the samples that, so you are taking 10 and we want to see if all 10 of them can be late stage tumors. So there are 15 of them. So your possible outcomes, your favorable outcomes, this is favorable outcomes, right? 15C10. So you calculate 15C10 and total is 25C10 and you just solve it, right? So it's 9 divided by 10,000, roughly. Okay. Okay. All right. So
the
this
previous
one's...
number of expected outcomes.
Hmm.
Can we write it for the expected outcome 10C5 plus 10C10 plus 10C5, madam, anything like that? The expected outcomes.
Why will be
Yes, we are
writing
drawing
that
only
way?
10. 10. We are drawing only 10.
So we are drawing 10 and we are interested in these
Instead
other
of putting
15.
the 15C10, can we do 10C5 plus 10C10 like that something?
No. So this number here, right? This 15 here, this is how many are we sort of the interesting group, so as to say, right? Which is this late stage tumor, which is 15. So out of those 15, any 10 we can choose. You remember the committee example we saw in the last week? There are 10 people, 3 of them are proficient in speaking, the remaining 7 are not. So what is the probability that you will make a committee? In that case, we say that there's a committee of 3 people, and what is the probability that all of them are going to be proficient in speaking? Or let's say we are making a committee of 3 people and maybe 5 are proficient, 5 are not proficient. So what is the probability that the committee of 3, all of them are going to be proficient? So it's like that. This is the total number. So you have 25 samples. You're choosing any 10 of them. And you are interested in the option, in the case that only out of those 15 tumor samples, what is the probability that when you choose 10, you only take out of those 15? Right? So,
but we are taking the last time they have taken from the the last example it was given. They're dividing the thing. Then they're giving that 10 only the top, ma'am, but it's totally taken sample.
So in the last time there was an extra information.
Okay.
So there was more information in addition to this one. Like let's say out of these 15 late stage tumor samples, 7 were from, I don't know, 7 were from females, 8 from males, maybe like sort of information. Here this is basic. 25 is 10 plus 15. And then you are taking 10 from 25 or you are taking 10 from those 15?
No,
Because
They're taking only 10 samples, madam.
Yeah.
Ma'am,
10th, what is the probability of getting other things among the 15? So 10 should be divided as 10C10 into 10C5, I presume, whether it's
No,
correct or not.
no.
Before
So
it's-
see, why are we taking 15? Here it's saying that late stage tumor, right?
Okay.
So late stage is this one, the
No,
remaining one.
totally it is 15 samples, ma'am. But we're taking only 10 items. Among the 10, it will be one time it will be 10 fully correct, and another time will be 5 may be correct, like that.
Yeah, that is true. So that is accounted here,
I
right?
thought 10C10 into 10C5 like that. Because
Okay, let me just explain you one thing here. So, yeah. So when we are saying this thing, right? When we are writing in this form, this is the total sort of total available, right?
yes.
And this number is how many you are choosing.
Yeah.
Right? So this is 10 in our case because we are taking 10 samples. And this one, when we are taking all the samples, like we are taking 10 out of 25. So in that case, it is 25. But when we are saying that we are interested only in the late stage tumor samples, then this becomes 15.
Okay.
So we are out of 25, we are choosing 10. That's what we are doing. And we are interested in some samples, so that's 15 out of, so that's like 10 out of 15.
Okay.
Right? So
thank you.
Yeah. Okay. Think about it again. In case it's still confusing, just take another example. Take the example of that committee or anything else. Maybe take like smaller numbers and you can manually write down all the possible combinations, and maybe that will make it clear. Yeah.
Okay.
Okay. So, okay. Now, in how many ways can the letters in the word science be arranged? So there is a direct formula which the solution here they have used. Yeah. So exactly. So I will tell you this. So once we see why it's this way manually, then we can also take a look at how the formula helps. So let's go to the slide here again. New slide. Okay. All right. So now this is the word, right? So in how many ways you can arrange it? So you have these 7 places. So you would expect that, okay, 7 factorial should be there. But now tell me, if I exchange the position of these two e's, I will still spell science, right? The word is still going to be the same. Isn't it? If this was E1 and this is E2, and if I write E2 first and E1 later, it's still the letter E, right?
2 times C and 2 times E are there.
Sorry?
By 2 factorial into 2 factorial.
Huh. So I'm coming to the factorial part, but so, right? So this E is the same. Likewise, it's the case with the C also. Right? This C and this C also. Now, so which is why, so that means you will ideally be writing, if you take factorial, you have calculated all the words twice in terms of E, right? Because you have, like science, you've written twice. There's another word. These were the positions of E. You counted this word also same, but it's actually the original word. So for E, you are actually dividing it by 2. And for C also, you have to divide it by 2. So this is simple to understand. Now let's say if there was another word. I am just writing a random word here. Let's say this is that word. Now, what is going to be the answer for this? We don't need to calculate it, but so what do you think would be based on this formula? So the formula says that on the numerator, we'll have that factorial. So whatever the number of letters are, the same thing. And then you divide it by some numbers. Now, what are those numbers and why did we? So 2 here is making sense. But when we increase it to something else, 3, 4, 5, do we divide it by that or do we divide it by something else? So what's the numerator here? It's the number of letters, right? So that's 8 factorial. And numerator, so you have E which is repeated. So
A repeated.
3 factorial and 2 factorial.
yeah. So now why do we have for 3? Why are we dividing it by 3 factorial and not 3? Like, are we dividing it
3
by
different
3?
positions of A.
Yeah, right. So I'll just for the sake of completion. So let's say this is there, right? So from factorial, we know how many ways can you arrange it? You can arrange it in 3 different ways, right? So 6 ways, right? I can write each of them. 1, 2, 3, 1, 3, 2, 3, 1, 2, 3, 2, 1, 2, 1, 3, and 2, 3, 1. These 6 ways, right? Likewise, this 2 is actually 2 factorial. This 2 is also 2 factorial, but it's just 2 factorial and 2 is the same. So it's not very clear why 2 factorial is used. But then here it's going to be 3 factorial. Okay. All right. Okay, good. So now you know what happened. Yeah. So now you know how such questions are solved. So now you can directly use, this formula is you can directly use. Simply divide by the factorial for each of the repetitive letters, and that factorial will be how many times the letter is repeated. And then you can solve it. Okay. Next question is that a researcher has mixed up fresh and old culture plates which have bacterial colonies. And there are 7 fresh plates and 3 old plates. What is the probability that the person is going to find all the old plates in the first 3 tries itself? Now this question is very similar to the one that we just saw, right? So you have 10 total plates, so you're taking 3 of them. So the total combinations are 10C3. And what is the probability that you will find the old plates? There are 3 of them. You have to find all 3 of them. So there is only one, in terms of combination, there is only one way of doing that. Right? So that's 1 out of 10C3. So that's 120. Okay. All right. Then next question is, so 70% of the plasmids that are used for bacterial transformation, they have been labeled using a gene. So in the plasmid, there is a particular gene that is there. So 70% are labeled and the remaining 30% are not labeled. And the transformed cells, so when the plasmid is inserted into a cell, it's said to be transformed cell. So now the cells which are transformed, only they will make a colony. The other cells, they will die. So mostly what is done is, just so that it's more clear, these plasmids, they would give like a, let's say it's an antibiotic selection gene. So what happens is, if the cell has taken that plasmid, the cell is now resistant to the antibiotic. So if you grow that cell on a plate which has antibiotic in it, the cell which has the plasmid will grow. But the cell which does not have this plasmid, it's going to die. So that's what it's saying, that only the transformed cells are going to grow on that culture plate. Now the procedure efficiency, that means when you are transforming the cells, not always will the cells get transformed. Only 75% of the cells get transformed. So now what is the probability of finding a colony which does not possess that reporter gene? So the probability of the plasmid being labeled, 0.7. The probability of plasmid not being labeled, 0.3. This is from this equation, this first sentence. And the probability of efficient transformation is 0.25, 0.75. Right?
Actually, I have a doubt here.
Yes.
Ma'am, when we are considering this 0.75, that is the transform cell.
Yeah.
So that can be also probability of the non-transform cell having the reporter gene. That is 0.25%.
Say that again.
75% are transformed genes, means transformed
cell.
cells.
Yes.
And the 0.25% have failed, but they
Yes.
would be also having the reporter gene.
No. No,
And
that
the
doesn't.
chances that out of the 75% of population which is there, okay, so there could be a chance of 25% which would not be having a reporter gene. I guess
Right.
that is what he wants to say. So, man, actually, I applied that insurance example in that adding the prone population with the probability plus adding the remaining population and that. So I was not getting the answer in this case.
Okay.
Now, if we consider that 0.25%, so that we get the answer of 47.5%.
Yeah, exactly.
Okay. No. So transformation means that the cell has the plasmid which has the reporter gene.
Okay.
Right? So
and then how?
Yeah, wait.
And then how it could be that if 70% of them have transferred, then out of those 75%, like then the non-reporter gene has to be from the other 25% or something like that.
Say that
Yes,
again.
ma'am, that will be the intersection for that both the probabilities of that 0.75% which are transformed.
Say that
and
again.
the 0.20 intersection for that transform as well as the non-transform, that is 25%, which we are getting from that 75% population which are transformed. So that would be like
transformed and non-transformed cannot intersect, right?
But the probability of having that with the reporter gene.
So the question is probability of finding a colony which does not have a reporter gene.
That will be that 0.25% may not contain also the reporter gene. No?
25 will not have the reporter gene also, and it will also not grow. So here the keyword here is colony, and colony is only given by those which are transformed.
Okay.
So the option is that you can have cells which are transformed without the reporter gene or with the reporter gene. That are the two cases.
Okay.
Right? So, right. So 75% is there, of course. So 75% of the population is only what you're looking at. Now, out of that population, 70% will have the reporter gene and the plasmid, and 30% will have the plasmid but not the reporter gene. So that is what this probability is here.
Okay, so I got confused.
So colony here means transformed cell.
So we should focus on that colony thing, that
So that's
only the transform things.
Yeah, so it's
ma'am, here I want to here I want to ask that when such questions come exactly, for example, when we have to consider that probability part of adding and not adding and just focusing on such stuff, because I also did the same way and I was repeatedly getting confused doing that. So I thought that I am not remembering or I have not got the concept clear or something like that.
So your argument is correct. So what that insurance idea that you have two options, right? It's like that complement, A with B and A with B complement, like that. But it's just this keyword colony.
Okay.
It doesn't just say cells, it says colony. And colony comes here. So that's why you have removed that second part. Thus, you're not adding any
Okay.
more information to it.
Okay.
Okay.
So, for example, if the same question was
Hmm.
transferred at probability of finding cells that do not possess a reporter gene, then we would have considered 75 multiplied by 0.3 and
yes.
25 plus 25 multiplied by 0.7.
And the answer would be 47.5.
Also 0.3.
Then that 25 would be as it is, I think.
Okay.
Right? Because they were not transformed, so they don't have.
Okay.
All of them don't have the reporter gene, right?
Okay.
So 0.25 plus 0.225.
0.25. Okay.
So that will be there. And then most likely this sentence would not have been given to you. This sentence, right? Because transformed cells, they have actually, only they are surviving on the plate. Because that plasmid, it actually has a, like, that antibiotic resistance something. So yeah, it's a slightly difficult question, but yes, you have to see. So mostly in questions, such extra information is only going to be given when it's going to be used. Yeah, so just think why have they given this information? Is it just to confuse you, or is it really going to be used?
Sure. Okay. Thank you.
All right. Okay. So to understand the sex dichotomy of autoimmune disorders such as lupus, the population distribution of healthy and lupus affected individuals is given in this. So this is the population distribution, right? Or demographics also can be said. So 47%. Yeah, so this is, so I think when you add the whole of it, is it coming out to be 1? I think so, right?
Yes.
5.2 and yeah, 4.8. Yes. So this is how you know that this is talking about the whole population. So in the population, there are 47% healthy males, 39% healthy females, 5% of the population are male with lupus, and 9% of the population is female with lupus. So these, yeah, so this is just like sort of getting the idea of what these numbers are. So what is the probability that a randomly selected individual is a female, given that they are affected by lupus? Now again, like we did that question of probability in 2 different ways, the card, drawing that card, here also I would like you to solve it in those 2 different ways, and we'll see if you get the same answer. Okay. Actually, there's just, yeah, no, we can actually solve it in 2 different ways. Yeah. So let me just go to the PPT here. Okay. So, yeah. What were the numbers? 49, 47, 39, and this was 9, right? Just let me check. 47, 5, 39, 9. Okay. This is in percentages. Yeah. Okay. So, okay, what was the question? A randomly selected individual is female given that they have lupus. Okay. So the probability female given its lupus. This is the case. Same as before, we'll first start off by writing the formula for conditional probability. Okay. Now, what is this value here? What number are we looking at? Females with lupus.
Total lupus would be the denominator and
0.48.
Sorry, what is the numerator here? F intersection L, female with lupus.
Being female and with lupus.
This numerator.
Being female and with the
9 by
lupus.
50.
So the numerator is
9
9,
by
right?
9 by
9%.
yeah.
And denominator from this table. So basically this is how you're going
14?
to, yeah. So this is how you read the table, right? It's a 2 by 2 table. So this means it's both of these cases. The 47 indicates male, healthy males. 39 here indicates females, healthy. 5 here indicates male with lupus. 9 here indicates female with lupus. And you can also find sums of each of the rows and sums of each of the column, right? So this column, it's adding up to 52. Sorry, this row is adding up to 52. This row is adding up to 48. What is 52 indicating? It's the male population, right? So 52% of the population is males and 48% of the population is females. That's one way of looking at it. And if you take it column wise, so this is 16, 86, is it? Yeah. So this is 86. 86% of the population is healthy. And this is 14%. So you can say 14% of the population has the disease. This is how you read such a table, right? So now the question was asked is, what is the probability that a randomly picked person is a female given that they have lupus? So if we simply go into this formula where you see the intersection, so intersection is basically one of these 4 values, right? Which is this, females, lupus. You see that particular row and that particular column. So that's 9 here. And the denominator is a sum. Can you see this? This whole second column is indicating lupus. So that's 14%, right? So you get 9 by 14. Now let's take a look at the other way. So like we discussed, what does conditional probability mean? It means that you have now reduced your sample space. So now you're only looking at a reduced space which has lupus individuals. So now you forget about this table. Now you have a new table with you. And this is that new table. Right? So now it is, so the total number is 14 here. And you're taking 9 out of those 14. So gives you the same number. Right? It's the same thing, same 2 different ways of solving it, like we did it for that blackjack question. Okay?
In this question, so where we are considering being female probability.
This one?
The question they are asking being female and the female
given lupus.
Then in this calculation, where we are using that being female probability.
So this is the probability, right? What is the probability of being female given that it's given that the person has lupus?
But the probability of being female in this given question is 39 plus 9, we will get 48%. We need to select the female, and that female should be with lupus.
Yes, so then we are only selecting 9. This 9.
Then where we are considering the female, madam?
This one, 9, because now your sample space has reduced to only lupus. Given that people have lupus, so you don't consider the healthy individuals anymore. That's what the conditional probability is, right? You no longer take these 39.
Instead of that table, if they give that 47 plus 5, 52 female, male, and 39 plus 9, 48 female are there.
Yeah.
And if they ask that how many members are affected in the female, how many members are affected with the lupus, then in that situation, definitely we need to consider total female. So we'll get 48. That means 0.48%.
I understand. I understand, but that is how conditional probability is used. Right? So there are 2 ways. You understand how this was derived, right? We've seen why this formula holds. Because you have actually...
Of course, but by taking that P of F by L, they are entirely considering the lupus population only. Why you are not considering the healthy with lupus female?
Because that is what the question said, right? Given that they are affected by lupus, so you actually ignore.
Female. Question is randomly selected individual is female and they should be affected with lupus.
So
But
the given,
individual females in the given population is 0.48.
I understand, but the formula is, or the condition is female given lupus. So you actually ignored this. You are only considering this now, right? The given that in conditional probability, the thing that has been given to you that has already occurred is now this. So you now no longer consider the whole population. That is why we do conditional probability, isn't it? Yeah.
So if we consider the female population, then I'm getting 31%.
Can you explain what you have solved?
So being female in that probability is 39.39 plus 0.09 will get 0.48.
Right.
Then having the lupus, probability of having lupus is in the entire population. The entire population having a lupus probability is a probability of lupus male and plus lupus female.
Which is
that
14%.
Is nothing but 14%. That means 0.14.
Yeah.
Then the probability of lupus with only female 0.09.
Yes. 9%.
Then in that case, female with the lupus is 0.09 into 0.48 by 0.14.
No. I think you're taking in terms of unitary method, but that will not be used here, right?
Same conditional probability only applied, madam.
Okay, wait. Can you tell it to me? I'll just write it here. Say that again. So
being a female in the entire population, so that is nothing but 0.39. That means 39 plus 9. So we'll get 0.48 probability.
So 48%. Okay.
48. Then having lupus, probability of lupus is male with female.
Yes.
Male and female. 14.
Yes. Correct.
And probability of lupus female.
Yes.
That is 0.09.
Yeah. Correct.
Then in the final condition as per the question, the female with lupus.
Female with lupus, nahi. Female given lupus. This. Right?
So we need to multiply 0.9 with 48 and divide with 14.
So, one second. So what have you written after this?
Like this is 9% and 9 into 48.
Oh, why will you do that? So you remember this formula, right? This formula. This is the conditional probability formula.
Here, based on the question, we need to consider the total female population also.
Listen, wait. So this is what is given. I agree. And this is what you need to find. You agree with this?
Yes,
this is what you need to find. Now forget the question for 1 second. When you are given this thing, this is your formula, right? This is the only thing that you solve in the formula. You put in the formula. Why will you change the formula?
We are not changing the formula, but we are considering all the given instructions.
You have already, so this 9% is already considering this internally, right? This 48 is what is, like out of this 48 is only 9, right?
Okay, you are getting that 64% answer.
That 9 by 14? Yeah.
So
9 by 14.
What that means 64?
So
female
it means
lupus.
No.
Female
So
given by lupus.
So given lupus. So now you forget this. Now you only consider this part. That is what it means given lupus. So the question means that if, let's say, if in a hospital there is a person. Yes.
That means like I just want to make for you. That means that out of lupus, now we are focusing only lupus. So for example, total number of patients of lupus were 14. So out of 14, 9 were females.
Yes,
so out
correct.
of total number of, if 14 out of 9 are females, out of 100, how many are females? That turns out to be 64% of total number of patients suffering from lupus in the hospital.
Correct. Exactly. When 9 out of 14 is there, given this table, so if you say in percentages, if there are 100 people, 64 are going to be females. That's unitary method. That is what percentage means.
Because here we are not talking about total number of lupus cases out of the total number of population.
Yeah, here we are only
because yeah, ma'am, answer is turning out to be 64. Considering the number here of females suffering as 0.9 comparing to the total population is very less.
Correct.
So we are not considering here about the total number of from total population. If it would be total population, then the answer would have changed to some 20 to 30%, 10 to 20% only.
Yes, correct. Because 0.9 is like just 1/10. 0.09 is 1/10.
Yeah, exactly.
Okay, fine. So we just have a couple of more questions. So
ma'am, if for example, if the same question is asked, if this is asked in table format, so should we consider that if they are telling 9, that means it is already taking about the intersection. That is where I made a mistake. I considered as I calculated a separate intersection, and then I got a separate answer. So I was confused whether I should consider 9 itself as an intersection or not.
Okay, so this is why adding all the 4 values is going to help you.
Okay.
Right, which is why we are adding it. And this actually means intersection. Table format means intersection. Female with lupus, not given. Male, healthy. Female, lupus, like that. All the 4 values.
And so if in the same case, if it would have been asked that considering female with lupus, like how many number of females are suffering from lupus from the healthy population? So how would we calculate in that case?
Say your question again. Lupus with healthy, like lupus from healthy population.
Not given lupus, how many, if we select the individual female out of total population, then how many percent would be suffering from lupus? Then how we would calculate the same question?
So that's only 9%, right? Oh, sorry.
Again,
no. So from the total population, female is 9%, right? 9 by total. And if you are asked, let's say, how many people are suffering from lupus, given that they are female, then it's
given from the total population, male plus female.
Then it's 9%. 9 by
9%.
Yeah.
Okay. But considering they are female, then we would have considered 39 as an option, or like how
so
then
9. Then it would have been 9 by 39. If it's
9 by
how many people have lupus, given that they are females.
Okay.
Then it's going to be in this axis. Yeah.
Okay. So 9 by 39.
Actually, it's going to be 9 by 48. 9 by 48. Females. Yeah.
Okay. So I guess sir is considering that scenario in his question.
Who asked the question right now?
I don't know.
Yeah. Okay. Yeah. Okay. Probably. I would like to skip to the other questions right now. If you still have a question, we can discuss this maybe in the next session, or we can discuss it over the discussion forum. Yeah, but I think we just for time we'll just quickly solve these also. So 10% of a given ethnic population contracted COVID-19, and a test has been developed to detect the antibodies. So now a test was found to be reporting false positive 2% of the time, false negative 2% of the time, and false positive 6% of the time. If you get back your results positive, what is the probability that you have COVID? Okay, so before we go into the details, a false negative means that the test result said you are negative, you don't have COVID, but actually you had. So it's a negative result, but it's an incorrect result. It's a false result. On the other hand, false positive means that the result said you have COVID, But actually you don't. In reality, you don't. But it said positive, but it was an incorrectly said result. So that's the result of false positive and negative. Now, so the population is infected. So it said that 10% of the population. So that's 0.1. So 0.1 was infected and a large majority is not infected. They're healthy. Fine. Now, out of the infected ones, when you test the infected people, the result will either come positive or negative, right? What do you expect the result for infected people? It should come out to be positive, right? So it comes out positive. So it's a, now here this is important. So it's a false negative. It means the actual people, they had a result. I mean, they had infection.
Out of 190 had 98 were positive, but
Right. 2%,
2% 100 were positive, but 2% were shown to be negative results.
Absolutely. That's the right way of putting it. Out of 100 people who were infected, for 2% of them, that is 2 out of those 100 individuals, the result came out to be negative. But they were all infected. Likewise, from the people who are healthy, 6% of them were said to be positive for COVID. But they were not. They were healthy. And the other of them are negative. Right? So now what is the probability that you have COVID-19? That you are actually if the results came back, if the results are positive, what is the probability that you have COVID? So now again, what is the, so you can do this in terms of conditional probability also, but I'll just tell you how it's written here. Oh yeah, it's written in terms of conditional probability, right? So let's define that conditional probability. So given the results are positive, what is the probability that there is COVID? So this also we can write in terms of that table. And we have this additional information also. So, so now the thing is, so what we are writing here is probability A given B. And here it's using an additional information. So we'll also go into that Bayes theorem right now. Right? So, so this, this is Bayes theorem. Now, what is A and B here? So probability of an individual being infected given they tested positive, which is what we want to find, right? So A here is being infected and B is testing positive. So now this is the formula. So we need to find out these 3 values here. So let's start off with the simpler one. So yes.
Just 1 minute. So what you applied here, P of A given B, it is a Bayes theorem. Same condition applied for the 8th question also.
Okay, that one. Okay, so let me come to it then.
Okay, first complete this one. We'll discuss.
Yes, we will discuss this. Fine. Now I understand. Okay, so now these 3 values we need to calculate. So let's calculate PB here. So PB means the probability of testing positive. You can test positive in these 2 ways, right? You are infected and you test positive, or you are healthy and you test positive. So simple, infected and positive, and healthy and positive. So you add these, you get 0.125. This becomes your denominator here. Now, what is PA? PA has to be the probability of being infected. Now, that is based on the population. So that's 0.1. So that number also we have. Now, the other question is, the other value here is probability of testing positive given the individual is infected. So probability of testing positive given the individual is infected is 0.98. So this is actually conditional probability. This, now you don't multiply this with this number. So this is conditional probability, right? So this one, 0.98. Now you have these 3 values, you solve. Okay. So be very careful in what you're calling. This is not just testing positive. This 0.98 is testing positive given you are infected. Yeah.
Yeah,
Just one
for
question here.
Sorry.
for the probability B, like, could you please explain, is there any straight formula for that?
This one?
This is the same question I had. Is there a generalized formula for calculating this?
This probability B?
Yeah.
Correct.
Okay, so this is testing positive, right? So it's you are testing positive in this case and you're testing positive in this case. So
Right.
so how did you reach to be positive? You were infected and positive, or healthy and positive. So just convert the statement from English to maths. Either infected and positive or healthy and positive. So infected
Okay.
positive means 0.1 into positive and healthy and positive.
Okay, yeah, got
Yeah,
it. Because because I missed that the negative. I was like, why
Yeah,
is
yeah.
0.4 is not considered?
Yes,
Because okay, it is
yes,
negative.
yes. Yeah. Okay.
Thank you.
All right. So before we go to the last question, I'll just come to this one here. Okay. So that means the formula that you are using is probability L given F, and this has to be what? L, right?
Probability of L by
And
probability of
sorry, F
Yeah.
and probability L. Right. So this one here is 48. This one here is 14. Yeah. But L given F is also not, you have not calculated that, right? This is not L given F. This is L and F.
You're having, madam, P of L 14.
Say that again.
P of L, probability of lupus, we are having already 14.
This is 14, this denominator. What about this?
That is nothing but female affecting with lupus probability.
No. See, female affected with lupus is intersection. Lupus given female is different. Like female given lupus is different. Right?
So if we consider P of A given B, A by B, then that is equal to P of B by A and P of A and by P of B.
This is A
P
intersection B, right?
B by A. B by A.
Solving. Yes,
As per Bayes theorem, so P of A by B.
So these are the two formulas, right? This is how you got this formula. Right? Because intersection is common in both of them.
So P of A given B equal to A given B. A given B equal to P of B given A into P of A
into P of A
by P of B.
Yes, correct. This is what I've written here, right?
Then the P of lupus given female will get
See,
0.09.
but 9% is not lupus given female or female given lupus. It is lupus and female. And it is intersection.
Lupus with female.
With, yes, not given. Okay. Yeah. Okay. So last question. Okay, I think this is a very similar question, right? So again, startup A, number of clients who order. Now this is numbers, no longer percentages. But I think for the purpose of this question, the total number is 100. So which is good that the number is 100. So you can consider these directly to be probabilities or percentages like 0.35, 0.1 and so on. But again, this is very important. These are numbers. Had it been adding up to like 200, then you have to divide each of them by 200 to get the percentages. So again, if a client is selected at random, what is the probability that they ordered antibodies given that they are ordering from startup B? Antibody given startup B, this is the formula, B and antibodies. So B and antibodies is this number 30. 30 divided by 100, which is 0.3. And then probability B is this whole thing. So 30 by 30 plus 25, which is 55. So 55 by 100. which is 0.55. So that's the number. Same question, same funda as question number 8. Okay. All right. So that is what we have. And yeah, so the deadline is 30th August, next Wednesday. Try solving the questions, the assignment. If we get stuck anywhere, post a question on the discussion forum. We won't answer the question, but we can clarify the question. And all right, that's it. We'll meet again for the next session. And just to remind you, there's another session going on Tuesdays. So the Tuesday before the Friday where this week was discussed. So next Tuesday we'll be discussing the next week. So Tuesdays and Fridays you're free to attend both the sessions, any one of them, whichever is more convenient. And either way, the recordings for both the sessions are going to be uploaded on YouTube, the link for which you will be able to access through the course page. Okay. So yeah.
Ma'am, one thing.
Yes.
So in the discussion we had that in assignment 1, question number 1, 4, and 8, will they reconsider this?
Okay, so I have asked those. I have not heard back from them on those. I will just ask them again.
And even in the assignment 2, 7th question also.
Okay.
Assignment 2, 7th question. In assignment 1, 1,
4, 8. Okay.
They
All
only considered in the assignment 3. They
yeah.
the 7th
I
question.
will inquire again. Sure. Okay.
Yeah, so before we end, so like I'll for the final examinations, how many questions would be there and the timing, if that?
Okay. I'm not familiar with that. I can ask if it's something. I think I think it's fixed, so I'll ask that. Number of questions and time. I'll ask that.
Thank you.
Yeah. All right. Okay. Thank you so much
Thank
for
you so much,
attending.
ma'am.
Yeah, it was a good
Thank you,
discussion.
ma'am.
Please continue like this for the subsequent 3 weeks also. All right. So I'll see you again next week. Yeah. Good night. Bye-bye.
Bye.